All right, video number 3. Here we go. There's just so much information for improper integrals. Sorry to make 3 videos, but this will be the last one. Okay, so we had just finished up, or almost finished up, this last example. I did integration by parts. Hopefully you got that down, you understood, you followed it. What I'm doing now is taking my original problem. I did the messy work here. This is all parts. I did the integration work. I have my antiderivative right here. So I rewrote the original. Then I set that equal to my antideriv evaluated from 0 to b, which were the limits of integration. Remember, we're sending b to infinity here. So now what I'm going to do is, where's my cursor? I rewrote it so there's no negative exponents. That's this step right here. And then I actually plugged b in for all my x's. I plugged 0 in for all my x's. Limit is still coming along for the ride. I have not done the limit yet. It's only after you plug in your limits of integration that you're actually going to take the limit. So now you're going to picture, all right, if I were to take infinity and plug it into here and here and here, those are the 3 places where I have an infinity. You might be thinking, oh, this would be negative infinity over infinity, but be careful. You have to remember that 2 times infinity, okay, that is, or negative 2 times infinity is negative infinity, but e to the infinity, exponential growth is greater than any other type of growth. Exponential growth is huge, whereas 2 times a number is just linear like that. So this is actually a smaller infinity over a huge infinity. A smaller number over a larger and larger number is actually going to be 0. I know it's weird to think about different levels of infinity, like a small infinity and a large infinity, but as you get to higher math, there are different levels of infinity. So this is going to go to 0. This one's easy, 1 over e to the infinity. E to the infinity, huge, that's 0. So I don't need to write limit anymore because I already plugged in. So I have 0, then obviously that's 0, forget about him, minus negative 1 over e to the 0. Well, e to the 0 is 1, so minus a negative is a positive. Whew, all that work, and we found out that this integral exists. The integral converges, and this area from 0 all the way to infinity on this graph right here, the area under the graph is actually 1. Example 6, I want to be quick. I'm not really going to spend much time on it. I wrote it all out. It involves u sub again. Again, it's the first type of improper integral where one of your limits of integration is 0. I'm going from 2 to 0. Just write this down. Obviously, don't write it down blindly. Notice what's happening here. I do u sub. I let u be natural log of x. And then du is 1 over x, which I have right here, dx. And again, notice what I did right here is I rewrote it all in terms of u, 1 over u du. These are still in x talk. I did an antideriv, which is natural log of u. These are still in x talk. In order to plug in my x limits of integration, I go and I take my u and I replace it with the x talk version. Then I plug in. Now, the last step I saved just to talk about here, picture plugging infinity in at this point here. This first thing depends on b. The second thing is just a constant number. Natural log of b, again, natural log, as b goes to infinity, natural log of infinity is slowly going to a larger and larger number. So that's infinity, this whole thing is. Then I have natural log of infinity again, which I just established is infinity. Doesn't matter if this is a number. This thing is infinity, so the whole thing is infinity slowly. So the integral diverges. The area under the curve is unbounded, and the limit doesn't exist. So we're going to get to the second type of, or I'm sorry, the third type of improper integral, which was this one right here, if there's an infinite discontinuity at one of the limits of integration. So we did a lot where we had infinity or negative infinity as an actual limit of integration. Let's take this one, which looks harmless at first, and tell you graph the function 1 over the square root of x, and realize if you're trying to go from 0 to 9, which is right here, I have a vertical asymptote at 0. So I can't back all the way up to 0 because it keeps going on forever. So we're going to deal with this improper integral and see if this area under the curve, which kind of goes up forever, if that is bounded or not, if the limit exists or not. Now, don't jump to conclusions here and say, oh, this is a p integral and p is less than 1, so it diverges. It is a p integral, except p is 1/2 here. It doesn't go to infinity. Remember, p integrals go from 1 to infinity here. So it is true that if p is less than 1, then it would diverge. However, we're going from 0 to 9, so that rule does not apply here. So we are still going to use a limit here. All right, anyway, back to filming. Just got a call from Quack. See to the right. You might be wondering, how are we going to involve a limit here? Now you have to remember, I'm going from 0 to 9. Like, I'm cutting this thing off at 9, so I shouldn't have green right there. So I'm only going to 9. This is the area that I want. Because the discontinuity occurs at 0, I'm going to think, all right, I need a limit as I get closer and closer to 0. And I'm approaching 0 from the right. So I go to 0 from the right, and I end at 9. So I'm going to not put a 0 there, because that's where the issue is. Wherever the issue is, put your new letter and send that thing to where it needs to go. Now, this is not going to infinity this time. It's going to 0 from the right. 0 to 9 of 1 over x to the 1/2 dx. Now let's go ahead and finish up the basic antiderivative stuff. So I bring x to the 1/2 in the numerator. I take my antiderivative. This is my antiderivative right here. And I haven't done a limit yet because I still actually need to plug in 9 and b. So I have 2 times 9 to the 1/2 minus 2 times b to the 1/2. So 9 to the 1/2 is 3. 3 times 2 is 6. This is just a number. It has nothing to do with b. Now I want to think, if I were to let b go to 0, basically just plug 0 in, this is going to be 0. So 6 minus 0 is 6. So even though this goes up forever and it seems like it would be an infinite area, it's actually convergent integral. The limit exists. This area under the curve is 6. Our last example is the last type of improper integral. So there's an infinite discontinuity within the integral. So this type right here, usually there's a vertical asymptote within your left and right limits of integration. So I'm going to go from -2 to 3 of 1 over x to the 4th. Now 1 over x to the 4th is drawn in red, not perfectly, but it's a sketch of it. I'm going from -2 to 3. There's a vertical asymptote at 0 right here that's cutting this area in half. So it looks like the area goes up forever. However, I need to break it up into 2 integrals at the vertical asymptote. You absolutely must do that, and you're going to use that property of integral that we used before to rewrite it. So I'm going to go from -2 to 0, and then from 0 to 3. Once again, you get 2 for the price of 1. Double the fun here. 2 different improper integrals. Again, there's no infinity at the lower and upper limits. The issue comes if I'm going from -2 to 0, that's this guy in green. -2 is good to go. It's the 0 that's the problem. You're going to approach 0 from the left here. And then from 0 to 3, that's in blue. 3 is good to go, but as I approach 0 from the right this time, that's where the issue lies. So we're going to have 2 different limits here. I'm going to use b and m again, so we're not mixing them up. And I'm going to rewrite them as follows. Here's how I'm going to rewrite it. Pay very, very close attention to this detail, which seems like a minor detail, but it's actually a huge detail. The issue in green, which is this one right here, and this bounded area, is at the 0, and I'm coming from the left. That's why I have from -2 up to 0 from the left. That's green. It's this guy. Then, as I go from 0 to 3, 3 is good to go. It's the issue coming to 0 from the right. That's on this side here. So that little plus and minus there make all the difference in the world. Now I have 2 different improper integrals. I'm going to do the same thing as I've always done. I'm going to do an antiderivative. Antiderivative of 1 over x to the 4th. Rewrite it. Add 1 to the power. Divide by the new power. It's -1 over 3x cubed. So now I'm looking at the limit as b goes to 0 from the left of -1 over 3x cubed from -2 to b. That's one of them. And then I'm going to add to it the limit as m goes to 0 from the right. Antiderivative is -1 over 3x cubed from m to 3. So now we can go ahead and plug in our limits of integration. What I did here is I plugged in b and -2, and then I plug in m and 3. And now I'm going to go ahead and clean it up just a tiny bit and think about what's going to happen when I plug in 0. Here's what I have when I simplify it. Now I'm ready to think about actually doing direct substitution with my limit. If I plug 0 in here and I plug 0 in here, I now have -1 over 0, which we know is infinity, and this would be infinity as well. It doesn't matter that this is okay and that this is okay. As soon as part of it is infinity, the whole thing is going to end up being infinite. That means that the integral diverges and the limit doesn't exist. So we have an unbounded area. It's not just a nice number that's finite. It's an infinite area right here. That means the area just keeps going up forever. It means that this curve is not close enough to the y-axis to go and converge. It diverges because of the way the graph grows here. It's an infinite area. All right, so I have, finally, we're done with the examples. Holy moly, there's a lot. So again, make sure you're clear on the 3 different types here of improper integral problems. I'm going to put up 5 problems for you to do. And then Monday, we will move on to series. All right, hope you have a great rest of the break. And good luck to our Moody's Mega Math Challenge team. Have an awesome time on Friday.